Hi guys, let's now look at directing effects in our EAS mechanism. If we look at this example here, if we have anisole and we nitrate anisole using nitric acid and sulfuric acid catalyst, that reaction actually gives three products shown here and the percent yield of each product. The ortho-nitro anisole product is formed in 45% yield. The para-nitro anisole product is formed in 55% yield. And actually only a very trace amount of the meta-nitro or 3-nitro anisole is formed in this reaction. So ultimately we have two predominant products. They're both formed in substantial yield. The ortho and para products. Thus, we call the methoxy group on the benzene ring an ortho-para director. It has directed the new group relative to itself to the ortho and para positions, not to the meta position. And indeed, many groups are ortho-para directors, like the methoxy group is here. Now, we'll need to look at each type of common group that may be on the benzene ring or any aromatic ring to keep it more general. And we need to determine if they are ortho-para directors or some other director. Now the other type of director, if we look down here, if we have nitrobenzene and we try to nitrate it, that is to put a second nitro group on nitrobenzene to make a dinitrobenzene product, we see that an overwhelming majority of the product ratio here is the meta-nitro product, the meta-dinitro we can call it. Now you do get, it is known that in this particular reaction, it's probably, the conditions are important, not shown here, but 7% yield of the ortho-dinitro product and 2% yield of the para-dinitro. But in this case, there's just one product that is substantially formed, and it is the meta product. Up here there were two, both ortho and para. And these two different types of outcomes are common with aromatics. Now here the nitro group is going to be called a meta director because it directed the new group meta. Now I happen to show nitration, and so we're ending up with two, but we could maybe be brominating here. And the bromine would end up meta to this nitro because a nitro group is a meta director, where the methoxy group is an ortho-para director. Those are the two types of directors. Now, as far as ortho-para, because you have two that are formed in substantial amounts, you will need to purify these, okay? You will need to do some maybe extensive purification to separate these two. Where down here, this reaction is more chemoselective. Groups direct meta, a single product is a major product. With ortho-para directors, you do have two products that are major products, and these may be tedious to separate. Now, we could say that actually para is a touch more favored. You can see that here. But what you don't see is that it's actually more favored than you think. Because if you look at this molecule, there's actually two positions that are ortho. And so because of there being two positions compared to being only one para, it's sort of twice as likely for a group to react at an ortho position. But even though it's twice as likely, you still get a little bit less in this example than the para. Now, in some other reactions other than nitration, sometimes para is preferred a little bit more than the ortho. But ultimately, we will always consider groups such as the methoxy, ortho-para directors. Both are going to be substantially formed. Okay. Now, how can you tell when a group will be an ortho-para director versus a meta-director? Well, if you know the activation-deactivation effects that we talked about and the groups over here, remember we had groups 1 through 4, yeah? Okay. We can use those same groupings here and we can say that any atom that can donate somehow to the ring, and in this case the atom bonded to the ring is an oxygen, if that atom can donate somehow to the ring, it will be an ortho-para director. Thus, groups 1 through 3 will be ortho-para directors. Because, as we went through these groups, we said that group 1, these are atoms that donate by resonance. Okay, so they donate. Group 2, these donated by weak resonance donation or inductive donation. Both of these are donating effects. Group 3. Now group 3, while they were net withdrawers, like a halogen, it's a net withdrawer. It does donate by resonance, and thus it does donate somehow. And groups 1 through 3, all of them donate somehow, and thus they're all ortho-para directors. Okay, that's what this says here. Now group 4, which can only withdraw, group 4, that is your meta-directors. And indeed a nitro group was group 4, right? We showed group 4. Nitro group was an example of a group 4. Okay, can only withdraw. In the nitro group we expect to be a meta-director, and indeed if you do this, this has been done in the lab, and the without purification the entire product distribution has been measured, and we see that the meta product is the major product. Okay, now in this table from the Smith textbook, this is not the Klein textbook, you see that over here they give you the directing effect. And all of those above here, okay, right, all of these here are ortho-para directing. This is groups 1, 2, and 3. And then group 4, okay, again, they separate group 4 based on if they're moderately or strongly deactivating. I did not do that. But group 4 are meta-directing. So that information was in that table. So, if we had this compound, the methyl ester of benzoic acid, and we brominated it using bromine and iron, which is a pre-catalyst, remember, these will react to form FeBr3, and then the FeBr3 is your Lewis acid. For coming back and catalyzing the bromination, we would expect the metabromo product to be the major product. Yes, we could get some of the other isomers, but usually you're asked to predict the major product, and that would be it there. All right. Another example here, if we take bromobenzene, and it looks like we're looking to iodinate it, iodine and an oxidant such as copper 2. What type of director is the bromine? Now again, if there was no group here, and you brominate this ring, you could put the bromine anywhere, and it's going to be bromobenzene. But since we have an existing group, we have to determine where the bromine is going to go relative to that existing group. That's what we're doing here. So where's the iodine going to end up relative to the bromine? Well, the bromine is a group 3. That's an ortho-para director. And we expect the ortho and para products as the two major products. Because the bromine does have a lone pair, and so it will donate by resonance. And any group that can donate somehow will be an ortho-para director. But why? We need to explain why, and the next pages do that. These are also from the Smith textbook we used to use. You should see similar explanations in the Klein book. And it all boils down to stability of the sigma complex. Okay? 3 different sigma complexes would be formed here, leading to each of these products. We need to look at the stability of each one. Now, in this example, the starting material is toluene with a methyl group. We can do our mechanism, okay? This arrow is not as precise as I'd like it to be, but we can attack and make bond between the orthocarbon and the electrophile, leaving carbocation here. Resonance looks good. All right. And then we eventually remove the H and restore the aromaticity. All right. And they've got the pi bonds moved around. If you remove the H here, you would get the pi bond here. But these are your 3 resonance structures. And if you look at them, right here we see this methyl group, and we can rationalize or explain the stability here, because this carbon inductively donates this sp3 carbon, and that's going to stabilize the sigma complex here. The existing group we see can stabilize the charge that occurs in the sigma complex. And they have this highlighted because this is the key resonance structure that you look at to see the stabilization effect of the group. Now if you do a para attack, you get your 3 resonance structures for your sigma complex. Right here we also see that that methyl group can stabilize the positive by induction. But if you do a meta attack and look at your 3 resonance structures, it turns out the positive charge never falls on the carbon where the methyl group is. And so you can never sort of make the argument of the sp3 carbon inductively donating to stabilize the positive. At least not as much as you can in these 2 reaction pathways. And so the intermediates leading to the ortho and para products, I called it plural, it's only one intermediate. The intermediate leading to the ortho or para products, or actually it's 2 if we refer to this intermediate and that intermediate, they're both more stable than the intermediate leading to the meta product. So these 2 pathways are going to proceed as the predominant pathways. Now you can note here that the positive charge when you're doing your resonance structure always falls ortho or para to where the electrophile is added. That's not something to memorize, but that's just kind of something to point out here. As you develop your knowledge, that'll kind of make more sense. You don't want to just be memorizing something that doesn't mean something to you. Okay, so the methyl group, as we would expect, because it's an inductive donator, is an ortho-para director. Now let's look at a group that has a lone pair, such as the amino group, aniline. We have an ortho reaction, meta, and para reactions. 3 resonance structures. The positive charge falls on the carbon with the group here. Now here, this is more than inductive donation. Here we can have resonance donation. We can actually move the electrons in and have an additional resonance structure. This is, of course, a stabilizing effect. The charge is delocalized not only around the ring, but also onto the nitrogen group. That key resonance structure is highlighted here. If we do a para attack, we see again we can get the positive on the carbon with the group, and we can do a resonance structure, and again we can get a key resonance structure here, similar to that one, where the group has donated by resonance. But if you do a meta attack, the positive charge never falls on the carbon with the group, and you're never able to use the nitrogen lone pair in resonance. So the meta pathway does not benefit from resonance from the existing group. And so the meta pathway is not going to be as preferred as the other 2 pathways. The ortho and para pathways are preferred. The amino group is an ortho-para director. Now this would be the same as the methoxy group in anisole. I mean, you could be able to do the same thing. Intermediate, you could use the lone pair to draw resonance structures to make the same argument. Now let's look at the nitro group, which we know is a meta director. We can show all 3 pathways. Okay. Now in the ortho pathway, the positive falls on the carbon where the nitro group is. Now I wish they would have shown some lone pairs here. I hate seeing charges without lone pairs. But what we see here is the positive charge falls or ends up being directly adjacent to a positive nitrogen. And that is bad. So in this case, the highlighted resonance structure is destabilized by the existing group. If the group wasn't there, it would actually be better. This group destabilizes the sigma complex. You also see the destabilization in the para attack, because the positive charge falls on that carbon and we have charges, positive charges adjacent. All right. But if you do a meta attack, the positive charge never falls on that carbon where the nitro group is, and you never get the bad effect. You never get the destabilization. And so by default, the meta pathway is better. Not because it's stabilized in somehow, but because it's not destabilized. And so with the nitro group there, the meta substitution product, the meta EAS product, is preferred. Now, of course, this same argument would apply to any group 4 group, and especially carbonyl, because remember, nitro tends to be sort of the default group 4 group that's often looked at, but in practice, There's lots of more examples of carbonyls, okay? And of course in the carbonyl, that carbon is partial positive. And if you had a partial positive, okay, let's redraw this. Let's put a ketone here. That's partial positive, right, because of the dipole with oxygen. If we had something that looked like this, we would see that that would not be good. You got a carbocation right adjacent to an electron-poor carbon. That electron-poor carbon cannot stabilize the carbocation, it actually destabilizes it. All right? Okay. Now, again, these effects are also additive, like we said for the activation-deactivation effects. But we have to consider the groups, and sometimes they may be reinforced directions or complementary. Sometimes the directions may be sort of opposing and we have to make a decision. Let's start with reinforced. If you look at this compound, well, let's call this paramethyl benzoic acid. The methyl group is an ortho-para director. The ortho position is here. The para position is already substituted. And typically you're not going to replace a group with another group. You could in some more sophisticated chemistry, but the first consideration are the unsubstituted positions. So the ortho position is available. Of course, that other ortho position is identical due to symmetry. So the methyl group is directing here, and the carboxyl group is a meta-director, group 4. It directs meta, also the same position. They're both directing to the same position, and so when we do this chlorination reaction, we would predict this to be our major product. Meta to the carboxy and ortho to the methyl. And if you wanted to practice some nomenclature, I would call this 3-chloro 4-methyl, that's one word, benzoic acid. One word, acid, 2 words. By the way, I'm calling it a benzoic acid, not a toluene. That's toluene there. If this was just a molecule, that would be 2-chlorotoluene or orthochlorotoluene. I just know that the benzoic acid group is going to take precedence over the methyl, and we'll name it as a benzoic acid. I would not expect you to know which group takes precedence in terms of a common name. But since I told you that, hopefully this name makes sense. And by default, that's the one position of the common name. Okay, next, opposing directions. We can explain this, but first look at the example. 4-ethyl anisole. Looks like we're trying to do a sulfonation to make a sulfonic acid. The methoxy is an ortho-para director. The ethyl group is also an ortho-para director. It's an alkyl group. It donates by induction. This oxygen donates by resonance. Well, it turns out that your strongest electron donator is going to be your director whenever you have opposing directors. Because if you look at this group is directing here. Ortho to that group, para group is blocked. This group is directing here, if we connect this bond. Ortho, the para position is blocked relative to this. So they're directing in opposing directions or different positions. But the rule is here, and we'll explain why, your strongest donator directs. And group 1 is a stronger donator than 2, and that's stronger donator than 3, and that's a stronger donator than 4, right? And so in this case, the methoxy is a stronger donator because it donates by resonance. And it's going to direct, and so the sulfonic acid will end up ortho to the methoxy group. The methoxy is clearly a stronger electron donator. Now if we go back over here, the alkyl group can stabilize the intermediate by induction. And you only get that if it goes ortho or para to the alkyl group. But the methoxy group can donate by resonance. All right? And which is a stronger effect. And you only get that if the new group ends up going ortho or para. You would rather get resonance stabilization. You only get that if we go ortho or para. The para position is blocked. We go ortho. So there's a clear winner there. Now, in the next example, there's not a clear winner. If we take, what are we going to call this? Probably, I'm actually not sure. It's either 4-hydroxyanisole or it's 4-methoxyphenol. I'm not sure which takes precedence there. For some reason, I think it's an anisole. It doesn't matter. Don't need to know that. But you do need to know how to predict directing effects. Now both are ortho-para directors. So the phenol group directs ortho and the methoxy group directs ortho. Now they're both group 1. And at that point we're not going to look any further. You could. But we're going to say that there's no clear winner to which one directs. And so I'm going to propose 2 major products. One in which the sulfonic acid is ortho to the methoxy, and one in which the sulfonic acid is ortho to the hydroxy or the phenol group. More likely to get mixture here, and you're going to have to purify this. It may be a little bit difficult to purify them. That's the issue you have to deal with if you don't have a clear major product. All right, let's try the next one. 3-chlorobenzonitrile. Wasn't benzonitrile on the nomenclature list? Actually, it was not. Maybe that's why I was pausing. I did not include that. When there's a cyano group, it's called benzonitrile. But that one is not on the list. Yeah. But anyhow, it is called benzonitrile. And so this molecule here would be 3-chlorobenzonitrile or metachlorobenzonitrile. If we brominate it, looks like we're brominating. Where do we expect the bromine to end up? Well, the cyano group is a meta-director. We should know that. It's a group 4, right? There it is. Cyano group, group 4. Of course, the halogen is a group 3. That's an ortho-para director. All right, which one's going to direct? The strongest donator. The strongest donator is the halogen. Now, it is a net withdrawer, but it does donate some, while the cyano group does not donate at all. Okay, the halogen, the chlorine is the ortho-para director. We have 2 different ortho sites because they're not the same. There's no symmetry this way. This ortho site is next to the cyano group, this one is not. We also have the para. So there's actually 3 different positions that this chlorine is directing towards. I show those products here. Now all 3 are likely products, much more so than the chlorine ending up here. You would certainly not predict it to end up here because the chlorine is the stronger director here. It directs ortho-para. Now what we can say here is that the first one is probably the least likely because the new group is having to sort of approach between 2 existing groups. And that site is going to be the most sterically crowded. Where this ortho site over here, it is next to the chlorine as well as that one. But over here it's more free because that H is very small. So in theory, these 3 are predicted. We can make an argument for why these 2 are favored and this one is less favored. And that's our theory. Now in practice, you may find out that maybe this one is predominantly favored for some reason. But we can't always predict that. Maybe after the fact we can rationalize it. But at the introductory level, we're not going to go that far with a prediction. A lot of times you see some interesting outcomes in real life. And there are some advanced arguments that we're just not going to make at this level. And if you go up, study advanced organic chemistry, you can get into some other arguments. Ultimately, we're talking about regiochemistry, and there's actually lots of advanced arguments for why certain reactions can be more regioselective than we would otherwise expect. Okay, a couple to do for homework here. This molecule is called vanillin. That's a common name. It's actually the molecule that's in vanilla wafers because this compound tastes like vanilla. Actually, natural vanilla is this compound, but the phenol group is bonded to a carbohydrate. What if we brominate vanillin? Where do we expect the bromine to go? And you do get pretty much one single product. We actually sometimes do this reaction in the Organic 2 lab. There's one major product here. The next one is interesting because we have 2 different rings. And here we want to decide which ring is more reactive. Then once we determine which ring is most reactive, we need to determine what position in that ring. And it looks like we're doing a nitration. Usually we are doing mono reactions. I'm not sure why I clarified that it's mono here. But usually we're always looking to do mono unless for some reason we are looking to do di or tri. So that finishes up directing effects. I'm sorry, let's call that more broadly, it's called substituent effects. There are 2 types of main substituent effects to consider. Activation, deactivation. Okay. And directing effects. Sort of looking at which ring reacts fastest is sort of a activation deactivation argument. Then we look at directing effects. Okay. Now at this point we will move back to reactions. All right. And we'll next be looking at Friedel-Crafts alkylation. And I'll make sure that this handout is posted. Let's see. We have an outline. Here we go. We looked at halogenation, sulfonation, nitration. We looked at reduction of nitro to amino. We've not yet looked at diazonium. We'll do that later. But what we're going to look at next is this, putting these R groups on, either carbonyl R or just plain alkyl. And this is called the Friedel-Crafts reactions, either alkylation or acylation. And the reason we had to stop and look at the substituent effects is because when we cover these reactions, we need to talk about substituent effects at the same time. So we'll get back to those reactions. Friedel-Crafts, it's in the outline here, but there's also a dedicated handout for the Friedel-Crafts reactions. This was the name of two chemists who collaborated to develop this reaction, discovered this reaction and developed it back in the late 1800s. It's one of the top 10 reactions in organic chemistry. Usually when reactions are named after the chemist, that usually means they're pretty darn important. Okay guys, we'll pick up there in the next video.